On-site vibration analyzer calibration, a webinar presented by the Modal Shop and PCB PIEZOTRONICS. My name is Mike Scott. I am the Industrial Product Manager at the Modal Shop, and today we'll talk about the technical concepts of how to calibrate a portable vibration analyzer on-site, either electrically or mechanically. This is the final webinar of the 2021 Industrial Market Series, again presented by Modal Shop and PCB PIEZOTRONICS. You can see the list of previous webinars there. All of these webinars are available on our YouTube channel, and I have a slide at the end of the presentation to showcase that. But you can always go back and rewatch any of these webinars on our YouTube channel. Just real quick on some of the topics, we have a digital accelerometer that turns your phone into a vibration analyzer. We talked about calibrating differential charge accelerometers on gas turbines. We talked about automatic tank gauging and liquid level measurements. We had a webinar February 11th on combustion dynamics. February 18th was wireless vibration monitoring, and last week my friend Mike Nero presented on 4 to 20 milliamp vibration transmitters. Some of you came to this webinar because you were invited by the Modal Shop, and some were invited by PCB PIEZOTRONICS. So let me just say something quickly about each company. But the Modal Shop is located in Cincinnati, Ohio. That's probably going to come into play later. And we are a world leader in metrology. We're a calibration lab here. We have a scope of accreditation on a2la.org and of course on our website with stated uncertainties. We manufacture calibration systems here, including the portable vibration calibrator. We also have rental, structural test products, and non-destructive testing systems. PCB PIEZOTRONICS is just outside of Buffalo, New York in Depew. It's about 10 minutes or 15 minutes the way I drive from downtown Buffalo. I'm a slow driver. I've been getting passed in the right lane a lot lately. I'm in the middle and people pass me on the right. I feel like I'm driving in Michigan where, school buses pass me. And anyway, PCB is just outside of Buffalo, New York. And it is might be the largest, I don't know if I can say the largest, but at least one of the largest piezoelectric vibration sensor manufacturers in the world. When I started at PCB, it was only one building. It was, let me try to use the pointer here. It was just the building that you see here. But now they've expanded to a machine shop that runs 24/7 in this building here. This used to be a wine wholesaler when I started at PCB about 16 or 17 years ago. But the building has really expanded. They also have manufacturing in North Carolina as well and some other places, but the vibration sensors are mostly made here at PCB in Buffalo and in North Carolina. It's completely vertically integrated facility where raw parts are coming out of the machine shop for advanced assembly under microscopes over here on the right hand side, and they make some of the best accelerometers in the business. Tri-shear, triaxial designs with full frequency sweep calibrations, which is going to come into play later in this presentation if I can just only get on my soapbox for a little bit. But the sensors made here at PCB are the best in the world. This is me. So yeah, what do I want to say? Well, I've been here at Modal Shop for 6 or 7 years now. I can't remember, it all blurs into one big beating. And previously I worked at PCB PIEZOTRONICS. So I sort of transferred within the company, if you will, from Buffalo, New York to Cincinnati, Ohio. Got out of the cold a little bit, got out of the cold and the snow. I did pass the Cat 2 vibration exam conducted by Vibration Institute. Dave Corelli was my instructor. And yeah, for 40 years, I've been a fan of some of the least successful sports teams on the planet. None of them have ever won a championship. So just recently, I got into Champions League soccer or European football, and my wife and I went to some games on a trip to England, and we watched the Premier League as well. And we just decided to be supporters of every good European football team that you can possibly imagine. And then so we just bought scarves for all of them. So I own like, I got PSG, I got Manchester City and Manchester United, I got Liverpool, I got Bayern, anything, you name it, I got it, so that whoever wins, we can celebrate and our team. As we're so tired of losing in all the other sports, I figured, why not just be a fan of all the best teams in European football, and then we can't go wrong. So that's how we decided to roll with it. So here at PCB and the Modal Shop, we understand power gen, we understand the industrial vibration monitoring market. We offer a lot of different solutions. Vibration monitoring, system verification, troubleshooting, the verification of alerts and alarms. We offer ground fault detection systems that monitor for stray current and poor resistance on a brushless generator. We offer troubleshooting for proximity probes, but we don't make proximity probes. Of course, we have combustion dynamics pressure sensors and industrial hygiene products. So there's a lot of instrumentation available through our group of companies for the industrial vibration market and for the specifically for the energy market, if you will, and oil and gas as well, both of those markets. So let's get into it. When we advertise this webinar, we somewhat playfully advertise this as ditch the service contract, but to be fair, product support plans offer more than just calibration and repair of the analyzer. And we're going to be talking about calibration of the vibration analyzer today. It doesn't mean that you can just ditch the service contract, if you will. It all depends. So most of the offering in a service contract centers around technical support, which the vendors like to break up into a lot of different variations to sort of bulk up the value prop of the plant. If you have a piece of marketing literature, there's going to be 3 or 4 bullet points just on support. It'll say, well, you can call whenever you want, you can email whenever you want, you can have access to self-guided tutorial where you can link up with other experts in the industry and share your, there's a lot of value there, but a lot of it's centered around technical support. Personally, I don't connect so much with the value proposition of the service plan. I've never really met with a vibration analyst that raved about the service plan, but I understand why, it's, I understand why people go for it. To me, it feels more like a necessary evil, if you will. All of the companies are doing service plans, so you don't have much of a choice as to whether or not you go for it. Because if you don't go for it, you might not be able to get the technical support when you need it. So just because you can calibrate your own vibration analyzer doesn't mean that you can ditch the service plan. And the support is certainly the biggest thing. To me, it's, I grew up in Buffalo, New York, and here in Cincinnati, it snows like once or twice a year. But every single condo downtown, I live right downtown, I got a condo, everyone we looked at had an HOA, a homeowners association, and part of what you paid for was snow removal. And it just drove me nuts because you pay $25 a month for snow removal and it only snows once or twice a year. I'm from Buffalo. I can handle the snow. I'll take care of it on my own. It's fine. So, it's difficult. You might say, well, I spent $300,000 on a dozen analyzers for my team. You know, why can't I get technical support? See, here I am getting on my soapbox again. So can you ditch the service contract? Not necessarily. It depends whether or not you value some of the other elements. Our goal in this presentation is to sort of teach you how you can do on-site portable vibration analyzer calibration and leave it at that. The goal of the webinar is to show you that element of it, and then it's kind of up to you as to whether or not you I think this is the wrong slide, actually. There we go. As smaller piggy bank, I wanted the picture on the slide. Up to you as to whether or not you still connect with the remaining elements of the value proposition if you take, for the service contract, if you take calibration and start to do it on your own. So if you can execute on-site vibration analyzer calibration, the elements in blue on the slide are suddenly under your control. Obviously, the calibration is done by yourself and would include the accelerometer if you went with the mechanical method, which I'll talk about later. And because you're doing the calibration of the analyzer on site, it doesn't need to ship anywhere, which depending upon who you use, it could take a long time for the analyzer to come and go. Now, sometimes they do offer a replacement analyzer while your unit is in for recalibration. And then, of course, from a tech support standpoint, if you can immediately validate the measurements that are being made by the analyzer, you do remove one of the failure modes regarding the acquisition of bad data. If you're getting some strange results, an immediate recalibration of the accelerometer, strange reader, and vibration analyzer could be useful to you as far as just making sure that you acquired quality data. The rest of the service contract, of course, remains in place. Technical support, e-learning, the self-help portal, etc. Sometimes you get analysis services, and of course repairs and cleaning of the analyzer itself. So whether or not you can save on the service contract kind of depends upon whether or not the OEM is flexible with that value proposition. Can you pay for certain things a la carte when you need them, or do you always need to buy the whole contract, whether you value it or not? Can you pick and choose the services that you offer? Can you have access to technical support without paying for calibration? You know, these are all questions that I can't answer, but you know, you can evaluate it with your service provider to see if maybe there's a cost savings to be had there. Can I really calibrate the analyzer myself? Yes, there are two methods. There's the mechanical method and the electrical method, which we'll talk about in a moment. But first, you should know that unlike accelerometers, there's no standard that governs vibration analyzer calibration. And the analyzer OEMs, you know, like SKF or Emerson, Allen Bradley, NTech IRD, whatever you want to call them, Azima DLI, A-, none of them are accredited for their calibrations. The analyzers can be calibrated in a lot of different ways. You could look at amplitude linearity, you could look at accuracy of the frequency measurement, you could do multiple points, you can do a single point, and that's part of the problem to doing it yourself. There's not exactly a blueprint for how to do it. The picture on the right, bottom right, is snipped right out of the ISO 16063 standard for accelerometers. So for accelerometers, there's actually a standard, and it provides a blueprint so that people have some instruction. Whereas with a portable vibration analyzer, it's kind of the Wild West in a way. And the OEMs are not consistent as far as what they provide on the calibration certificate, and a lot of people just want to default to sending the analyzer back to the OEM, and I can't blame them. You know, people do the same thing here with the portable vibration calibrator that we manufacture. They always send it back to us for recalibration, and we are accredited for that, but even if we weren't, people would send it back to us for recalibration because we're the experts on it. And that, you know, that's part of the value proposition from the OEMs is they are the experts on it. They understand how to adjust it if it's off, and they can just duplicate the original calibration that they performed on it. So it's both a curse and a blessing to not have a standard, because you can look at your analyzer. It gives you the freedom to look at your analyzer and calibrate it how you want to calibrate it, specific to how you use it. But at the same time, it leaves open to interpretation. The fact that there's no blueprint can certainly make it intimidating to calibrate the portable vibration analyzer. So what are we actually doing when we calibrate a vibration analyzer? Are we calibrating or are we just validating? Well, it kind of depends what you do. Calibration implies that an adjustment can be made to bring the device under test within tolerance versus a more accurate standard. Like, for example, a heart pressure transmitter can be trimmed or adjusted to be brought back within tolerance. That scale on the top right, that has a 0 button on it somewhere. The reset button is the 0 button. Whenever you press that button, you're calibrating it. You're calibrating it with 0 payload. You're teaching the shaker what the scale what 0 payload is, and you're calibrating it. So in the case of vibration analyzers, when we calibrate the entire unit as a system, accelerometer and analyzer, which I'll show in a second, if we make an adjustment to the input sensitivity of the vibration analyzer to match the output of the accelerometer, then we're actually doing a calibration. If we don't make any adjustments, we're really just doing a validation, and a validation is done when the unit under test is compared against a more accurate standard, but is not adjusted. And an example of that, both of these things come into play in the vibration market. Piezoelectric accelerometers are generally uneconomical to adjust. So in the world of vibration, we actually use the word calibration all the time when we kind of mean validation. But it's just so commonplace to say calibration here in the vibration world. When an accelerometer comes in here, for example, to the modal shop, we offer calibration services. We don't say validation, even though maybe that's the more accurate word, because we're not going to open up the accelerometer and make any adjustments to it if it doesn't pass calibration or if it's off by whatever percentage, 3 or 4%. It's not like we can bring it back to where it's dead on 10 millivolts or 100 millivolts per G. That's just uneconomical to do. So the terms are kind of interchangeable in the vibration market. To open up a vibration sensor would involve obviously opening it up. It's a hermetically sealed sensor in most cases, so to open it up is difficult in itself. And then the picture on the bottom right there is a tri-shear design. The sensing element is located between those 3 masses that you see around the preload ring. Loosening of that ring is one of the primary reasons for signal drift, but to get in there and actually make the modifications to bring the sensor within tolerance is generally uneconomical. It's cheaper just to buy a replacement sensor. So electrically testing a vibration analyzer would be an example of validation. This is electrical analyzer calibration in a sense. A function generator is used to simulate the signal from an accelerometer and compare it to the measured vibration levels on the analyzer. So we'll use a function generator like that Tektronix. We'll measure the output independently using the Agilent DVM that you see just below it. Depending how many channels we do, we might use the whole stack of Agilent DVMs. On the plus side, electrical analyzer calibration can be accomplished with, you don't need a shaker, you just use a function generator or a simulator. And the uncertainty is a lot lower because there's no mechanical motion. The uncertainty of, in general, if you look at various scopes of accreditation, the uncertainty of AC voltage, DC voltage, frequency measurement is much lower than the uncertainty of mechanical accelerometer calibration. So there's no moving parts in this system, which allows you to have very low uncertainty of measurement, where on a mechanical side, you have to deal with distortion and transverse motion and things associated with that mechanical motion of the accelerometer. Also, it allows, so one of the cool things you can do with electrical analyzer calibration is actually simulate advanced vibration faults to test the processing algorithms for, like, a lot of vibration analyzers have stuff. There's a lot of marketing terms out there like peak view or spike energy, where they're going to do some advanced signal processing to try to pick up at an early stage bearing faults or gear mesh, stuff that can be hidden in the overall vibration signal. Just pull that out of the FFT, separate it, and present it to the user. So that's a really nice feature of a portable vibration analyzer. You could actually test the accuracy of that methodology using electrical analyzer calibration. That said, you need to have a very thorough understanding of how that methodology is applied in order to do that. And it doesn't help that the analyzer OEMs typically do not perform that type of testing, but it would be really cool if they did. On the downside, the accelerometer is not tested, so it's not a complete test of the measurement system. And you have to keep in mind that your accelerometer is probably the weak point in the system. It's the element that's more likely to fail, and it's the only part of the system that actually is touching the machine. As I mentioned before, it does take an understanding of how to correlate voltage to vibration amplitude. Like, we calibrate ComTest, that's a vendor I didn't mention yet. We calibrate ComTest vibration analyzers here, and we apply a voltage that's easy to convert to inches per second. We just pick a frequency. It's 159.2 is the frequency at which velocity intersects with acceleration. So if you apply a signal at that frequency, it's a 1-to-1 conversion. So let's say it's an analyzer set up for 100 millivolts per G. If I apply a 100 millivolt AC signal, I'm applying 1 G. And if I do it at 159.2 hertz, I'm also applying 1 inch per second. So that's kind of how it goes. On the final con is the analyzer adjustment most likely requires OEM intervention or someone qualified to open up the analyzer and make an adjustment. That said, it's somewhat unlikely that the analyzer is going to require adjustment. Mechanical analyzer and accelerometer calibration involves using a shaker. Doesn't have to be the portable shaker table, any shaker. Using a shaker with a known vibration amplitude to test the vibration analyzer by exciting the connected accelerometer and measuring the deviations. And on the plus side, it tests the accuracy of the accelerometer and analyzer as a system. And it does allow for calibration or adjustment of the vibration analyzer to match the accelerometer's output. And it can be a little bit more simple because if you have a shaker that gives you the scale of the amplitude of vibration, you can do the calibration in the same scale, so you don't have to convert units or worry about what frequency you're at. That all depends upon what shaker you use and what you use to measure the known vibration on the shaker itself. On the downside, you really can't. Well, you can. If you could use like a new shock or a shock tower or something to generate really high frequency vibration signals from the accelerometer, and then see if that applies to the advanced signal processing methodology. It's just very difficult to do. And it might take some specialized equipment depending upon how high you want to go. And of course, it has a higher uncertainty of calibration when you're doing a mechanical calibration. Why should the accelerometer be tested? These are some of the general traits of the accelerometers that are supplied with a portable vibration analyzer by the OEM. Usually those sensors are only calibrated at 100 hertz, but we use them throughout their frequency range, but they're not calibrated throughout their frequency range. It's a single point calibration, which is not ISO 16063 Part 21 compliant. Typically, the frequency response is plus or minus 3 dB, which converted to percentages is surprisingly high and low. It's 41% high, 37% low. And, you know, the vendors, they do that because it allows them to specify the highest frequency response. It's a very competitive market. So in general, within the industrial market, plus or minus 3 dB has become the standard. When you're advertising an accelerometer, you'll say, oh, it's good to 15 kilohertz, plus or minus 3 dB. Where in the test market, they don't do that. Usually the sensors are good to 10 kilohertz, plus or minus 10% or 5%. 3 dB is not really used in the R&D market as prevalently as it's used in industrial. So it's sort of become a specsmanship thing. And like I said, the accelerometer is not calibrated throughout its frequency range. So you may be depending upon an accelerometer to make a measurement at bearing fault frequency or gear mesh, but it hasn't been calibrated anywhere near that frequency. See, I told you it's going to be hard for me to stay off my soapbox during the course of this presentation. So you have to pay attention to the usable frequency response of the accelerometer and just be aware of what plus or minus 3 dB really means. It's a small number because no one wants to see 41% high or 37% low. So they use 3 dB. They use it for marketing purposes. And you know, the company I work for does the same thing. Sensing element on these sensors is ceramic. Ceramic elements are artificially polarized and they are more apt to drift over time than quartz. So some of the reasons, you know, and I've been doing this a long time, 16, 17 years. I have used the Emerson 2130, 2140. I don't think I ever had a 2120 in my hands. CSI Emerson, Rockwell NTech, IRD, Allen Bradley, whatever you want to call them. I did some troubleshooting with the DataPack 1500 before, which is a real old one. I've used ADASH, SKF, Proof Technic. Proof Technic was interesting. I'll talk about that in a second. I want to get off track. And Comtest. And the only analyzer where I was impressed with the accelerometer itself was actually a Zima DLI. They had a triaxial accelerometer with a full frequency response sweep calibration on all 3 axes, which I thought was fantastic. That one kind of set itself apart. Otherwise, in general, you can expect 3 dB tolerance, ceramic element. They're all ceramic, even the Zima DLI one, and just a single point calibration at 100 hertz. This is the SKF. This is just an example of what I'm talking about. The CMXA 80 is supplied with 2 CMSS 2200 side exit accelerometers. So how do we look at this specification? First of all, we see 100 millivolts per G sensitivity, and we can see that the precision is plus or minus 10%. Usually this type of tolerance is going to immediately follow this number or be on the line directly below. So for this accelerometer to pass calibration, and down here, I blew these notes up. These are kind of the fine print. It's only calibrated, they don't explicitly say it, but it's only calibrated at 100 hertz. So in order for this accelerometer to pass calibration, it needs to be between 90 and 110 millivolts per G at 100 hertz. It's not calibrated anywhere else in its frequency range. And you can see they do give you the 10% range, tolerance range to 5 kilohertz, and the 3 dB range to 10,000 hertz or 10 kilohertz. So just an example of what is typically supplied. I don't mean to pick on SKF. I could have pulled up Emerson and given the same example. But you know, usually it's going to have kind of a wider tolerance, you know, of 10% or maybe even higher. And it's a single point cal. And then, of course, you have the 3 dB range, a little bit deceiving there. So in the case of this transducer, if you had a lot of SKF analyzers, you know, technically, hopefully this doesn't happen, but technically, if you had 10 analyzers and 10 sensors, you might have some sensors that are closer to 90 millivolts per G. You might have some sensors that are closer to 110 millivolts per G. So if you interchange those sensors, and maybe the last quarter you took data with a 90 millivolt per G accelerometer, and then this quarter you're using something that's 105 millivolts per G, your vibration trend automatically going to be 15% higher if that's a scenario. So it can be tricky, and if you're in the market for a vibration analyzer, it might be in your best interest to look for one that, or just buy the accelerometer by itself, or you can get one that's plus or minus 5% or something a little bit tighter. Okay. So that being said, so the accelerometer's got a pretty wide tolerance. Should I adjust my analyzer? That's a question I get all the time. It can be difficult. I want to say yes. I mean, in the perfect scenario, okay, everyone would quickly run a sanity check at least on the accelerometer before they go out and they do data acquisition. And to do that, you don't have to spend an arm and a leg. You can get a simple handheld shaker like the one I have on the screen, and if you want to use a separate power supply and a voltmeter, that battery powered signal conditioner is like $200, somewhere in that range. Actually, that one specifically has gain, but they have cheaper ones than that. And you can excite the accelerometer at 1G at 159.2 hertz and just quickly get a sanity check on the sensitivity of the accelerometer before you go out and make vibration measurements. Should you change the setup? I can't really answer that question for you. That kind of depends upon your program, because there's pros and cons. I mean, if you take the time to program the exact sensitivity at 159.2 hertz of your accelerometer, it's more accurate than not doing it. But you have to remember that now that accelerometer and analyzer are paired as a system. So if people mix and match their accelerometers, or they pair a different accelerometer, now your system's going to be off. So I guess it would depend upon the tolerance of the sensors that you're using. If everything that you have has a plus or minus, at least a plus or minus 5% tolerance at reference frequency, and remember that's only at reference frequency, but for simplicity of the conversation, we'll just say plus or minus 5% at reference frequency, which is usually 100 hertz. If everything you have is 5%, maybe it's not worth it. The worst case scenario, you grab a sensor that's 95, and then the next time you grab a sensor that's 105. If you're using sensors that are 10, 15, or 20% tolerance, then I think there's more value in checking them before you go out. And of course, you can go out and acquire, for not too much money, sensors that are more accurate. Not to toot our own horn here, but the precision sensors that are made by PCB, they advertise a 5% tolerance, but when they make them, they generally turn out a lot closer to 100 millivolts per G. The specification, I would say, is conservative, because what happens is they actually do a pre-calibration on those, and so they'll put them on a shaker just at 100 hertz. Now, I'm not saying they're going to do a full sweep pre-cal, but they will build the sensor, try shear design, and then they'll tweak that design before they seal it up so that they have the best chance of being dead on 100 millivolts per G at reference frequency. And then that also gives them the best chance of passing the calibration process throughout the frequency band. So might want to think about, if you acquire really good sensors, you have less to worry about here about adjusting your vibration analyzer. So it can be a slippery slope. I like it in theory, but if it's forgotten about and then someone goes to use that analyzer and it's set up for a 90 millivolt per G, like in the picture I have it set up for 90 millivolts per G. If I forget and I go and I use it with a more sensitive accelerometer, then I'm not going to get good data. So you know, there's a trade-off there. Also, not every analyzer can be adjusted. I forgot to mention that. That's where that proof technique analyzer comes into play. I had the proof technique analyzer in my hands, and in order to make an adjustment to the input sensitivity of the accelerometer, I needed a special passcode that my customer didn't have the code. It seemed like they had to call the vendor to get it. So I'm not 100% sure if they give you the code in the manual with Proof Technique, or if you have to call them to get it, or even if they will give it to you. But not every analyzer is adjustable from my experience. Let's talk a bit about the mechanical comparison method before we sign off for the day. So the mechanical method is using a shaker like you see in this picture. We're shaking at 10 Hertz, so it's easy for everybody to see. We're going to use a shaker to excite the accelerometer connected to the vibration analyzer, and just use the comparison method to, in this case, we're shaking at 0.81 Gs. Is the analyzer going to measure 0.81 Gs? So that's what we're looking for in the comparison method. So it's really simple. It's a one-to-one comparison. And in this method, like I said, and here's an example where we were shaking at 1.5 Gs peak at 3,000 cycles per minute. I was using a digital accelerometer in this case, and I took the FFT on the digital accelerometer, and my peak was at 1.549 Gs, and it did occur at 3,000 cycles per minute. So I had a little bit of error there, which would be 1.549 minus 1.50 divided by the known of 1.50, essentially gives me my error in this case, which I should have done the math on, but didn't do in advance of this presentation. It was a little high. It was in the, I think that's in the 10% range as far as the error goes for this particular measurement, or close to it. And then in, here's another picture of the comparison method just using the Emerson 2130. I'm shaking at 0.2 inches per second peak and at 30 Hertz, and it's kind of hard to see because the numbers are so small. I had to get this image on the slide, so it depends on your screen resolution, but you can barely make it out. The amplitude in the bottom left of the analyzer itself was 0.197 inches per second, so I was only off by 0.003 inches per second, so this was very accurate, and my frequency was 30 Hertz, so again, 30 Hertz was dead on versus my known that was coming from the shaker table. And like I mentioned earlier, there's a variety of ways to calibrate a vibration analyzer. You could go for linearity, and no one's going to tell you that that you're doing it wrong or doing it right. There's no standard. Like I said, it's the Wild West a little bit. So this is just an analyzer example here in linearity, where we started down at 0.25 and we measured the linearity of the amplitude measurement, holding the frequency of the linearity and going all the way to 3 Gs peak. And then here's that same data just broken out for accuracy. So in this case, it was very linear the entire time, but my measured values were usually about 2.5% higher than my known values. So I have my known values here on the left. I have the measured values here on the right, and my deviations, like I said, that's measured minus known divided by known, expressed as a percentage. And so each of my measurements were about 2.5% high. As far as frequency goes, this is just my experience. Very rarely is the frequency incorrect. I seldom do I see any deviations on the frequency measurement on a vibration analyzer. Some people might have a different experience, but that's just my own personal experience. It tends to be right on. So, but you can measure, of course, the accuracy. We depend upon accuracy of frequency response measurement in the analyzer, so it's not a bad idea to test it. I just think it's one of those things that's probably unlikely to fail. Your most likely inaccuracy is going to be on the amplitude side of things. This is my favorite way to express the data. This is what I would recommend testing over the usable frequency band or your frequencies of interest. And in this case, I stopped at 1,000 hertz. You could go higher, of course. I was doing this in inches per second peak. It was a little bit sloppy on my part. I didn't note that in the amplitude scale here, which I should have done. But you can only go so high with a shaker table in inches per second peak. So I stopped at 1,000 hertz. And in this case, we just have the measured amplitude here, measured frequencies here, and of course your knowns over here, and it'll calculate the deviations for amplitude and frequency on the right-hand side. I would have loved to hold the amplitude at a 1/2 inch per second peak throughout these frequency response points. But the shaker itself is difficult. It's difficult to stay in the scale of inches per second. It's difficult to hold at 0.5 with a shaker. The higher and higher you go, the more stroke you need. So it starts to become difficult to keep that at 0.5 inches per second. Whenever you do a vibration analyzer calibration, I do recommend documenting the analyzer settings. And your window type can, of course, affect your, this isn't my field of expertise per se, but the way it does the frequency responses in bins. So your window type certainly affects the bins. And flat top window is probably the best one for pure calibration, but I'm not saying you should calibrate it in flat top if you're going to go out and use it in Hanning or Hamming or something else. You should calibrate the analyzer in the window that you intend to use it in. But documenting, the important thing is documenting the results is critical, because if you happen to go out on a route and take bad vibration data and you want to know, it just gives you that documentation where you can compare the settings on the analyzer versus when it was calibrated. That's kind of the key. So be sure to document your results. And of course, document your test equipment. And this is very important for the accelerometer that's paired with the vibration analyzer. In this case, it was a CSI triaxial accelerometer. Document the serial number, the date that one was calibrated, the sensitivity at 100 hertz, etc. Make sure that information is documented on the calibration report, and that way, if someone happens to swap accelerometers and the data becomes strange, you'll have a record of what accelerometer was paired with the analyzer when you did the calibration. A cheap plug here. All of the charts and graphs that you just saw in the last 4 slides, they are supplied with the workbook that is supplied with our portable vibration calibrators. A little bit of an advertisement here. My apologies, but the portable vibration calibrator does come with a workbook that allows you to create the linearity, frequency response, accuracy charts that you just saw in the last 4 slides, and of course document the settings and document the equipment that was used to calibrate the vibration analyzer. We didn't do anything revolutionary per se. We just, people have been performing system testing and calibrations on analyzers for a long time. All we did was add a report, kind of using our background in calibration. We added a report that people could use to create their own calibration certificates and sort of remove that hurdle from the process. Like, I want to do this, but I don't know how to get started. Well, the report helps you, and we also have instructions in the manual, but the report helps you to get started with the process if you're interested in taking this on your own. And I'd like to point out that the portable vibration calibrators are available for rental as well. A lot of people only need to use these calibrators once a year. You might, you use your analyzer every day, but you use the calibrator once a year, and you might calibrate the analyzer once a year. So they are available for rental because you're only going to need to use it once a year if you're just calibrating an analyzer. So it can be a big cost savings if you are maybe able to change that service contract or modify the service contract to save money there, because renting the calibrator is very inexpensive. Okay, I would encourage you to watch our full-length video if you're interested in how I calibrated the CSI 2130. This video is on our website and it's on our YouTube channel. It's called Field Calibration of Emerson CSI 2130 Vibration Analyzer. I go through the whole process of doing a, I guess I'd call it a frequency response calibration in the scale of inches per second peak. Okay. Wrapping up, this was our webinar series from the end of 2020. If you go to our YouTube channel, you can see the all of these webinars are posted. The video recordings of each of these webinars are posted. So we did high temp turbine vibration sensors. We did troubleshooting shutdown alarms. We did noise exposure and noise dosimetry. Trying to go a little quickly here. Ground fault monitoring on brushless generators, human vibration measurements, and the importance of that last one. I really enjoyed the combustion dynamics pressure sensor calibration, but we also talk about accelerometers in that one as well. If you go to our YouTube channel, we have all of the webinars in playlists. So you can click on playlists and you can see the whole series from the fall or winter time, if you will, of 2020, and the current series as well, springtime 2021 for the industrial vibration market is up there. This is the final webinar in the series. Like I mentioned earlier, we did our digital accelerometer, we did the calibration of differential charge, we did liquid level measurements, combustion dynamics pressure sensors, wireless vibration, and 4 to 20, and this is the final webinar in the series. And again, all of these webinars are on our YouTube channel. I hope you take a minute to check them out. That was fun. I hope I didn't get on my high horse too much about some of the sensing technology that's supplied sort of by default with the analyzer OEMs or the service contracts. Just want to give people the option and maybe show how analyzer cal can be accomplished in the INC shop or in the reliability department if the customer so chooses to do so, the main goal. So I want to thank everyone for taking the time to attend today's webinar. I hope you enjoyed it. Hope you learned quite a bit. And again, if you would like to have us send you a certificate for continuing education, please let us know. We are happy to do that. You'll get it right away. And thanks again.